Okay, section 5.2.2, what is a logarithm? Defining the inverse of an exponential function. You have learned how to undo many different functions. However, the exponential function has posed some difficulty. In this lesson, you will learn more about the inverse exponential function. In particular, you will learn how to write an inverse exponential function in y equals form. So, ideally, this would be done with a silent board game activity. Your teacher would display the table to the whole class, and while working together, you would complete the table. See which ones you can fill in. So, looking at this table and knowing what we've been studying so far, can you figure out what's going on? When would x equal 8 and y would end up equaling 3? When would x equal 64 and y would equal 6? When would x equal 1/2 and you get an answer of -1? So I'm going to slowly start filling these in. See if you can figure out what's going on. Okay, so hopefully you were able to see what was going on there. We'll look at it a little differently. 2 cubed makes 8. 2 to the 5th makes 32. 2 to the -1/2 makes, 2 to the -1 makes 1/2. So 2 to the g of x is giving me the answer of x. 2 to the 4th is 16, 2 squared is 4. When I get to 3, I need a calculator. It ends up being 1.6, but we wouldn't ask you that one. 2 to the 6th is 64, 2 to the 1st is just 2. 2 times itself never is going to give you 0. Does not exist. 2 times itself, 2 to what power makes 1/4? I said 1/4 because it's 0.25, right? So 1 over 4. So -2, because 2 squared is 4, and the negative makes it 1 over. 2 times itself is never going to be -1. And again, this one you would need a calculator for, -2.3. So describe the equation in relation to x and g of x. So that's what we did. 2 to the g of x equals x. Look back at our ancient puzzle problems. If you've not already done so, write an equation for g of x. So remember, log base 2, because the base is 2, and then of x, that's going to equal g of x. It gets the exponent out of the air. Logarithms get the exponent out of the air. Why is it difficult for 0 or -1? Because 2 times itself can never be 0, and positive 2 times itself can never be a negative number. What is the output for x equals 25 to the nearest hundredth? Let's not even do that, because we would need a calculator to do that, and that's not what we're focusing on this class. Another ancient puzzle. Lynn is supposed to fill in a table for g of x equals log base 5 of x. Oh, okay, so they tell us it's log base 5 of x. She thinks she can use the log button on her calculator, but when she tries to enter 5, 25, and 125, she does not get the outputs in the table below. She is fuming over how long it's going to take her to guess and check each one, when her sister suggests that she does not have to do it for all of them. She can use what she knows about exponents to fill in a couple more, and she can use guess and check for the others. Discuss with your team which outputs can be filled in without a calculator. So they tell us it's base 5, and you guys should be memorizing your bases, your exponent problems. So I know, for example, 5 squared is 25. They already have that one filled in. 5 cubed is 125. Times 5 one more time to the 4th power is going to be 625. I also know 5 to the -2 equals 1 over 25. That looks like that's all the ones we're going to be able to do without a calculator. With your team, use your calculator to estimate the remaining values. So go ahead and find a calculator. You're typing in 5, and then you're guessing a number, guess a decimal, until you get an answer of 1/2. And then do 5 and guess a decimal until you get an answer of 2, etc. Pause your video. Okay, so I filled them all in. C, what do you notice about the results for g of x as x increases? So x is increasing pretty quickly, right? 1, 2, 3, 4, 5, 6, 7, 8, 10, 25, 100, 125, 625. But now if you look at the g of x numbers, negative 2, negative 1, negative 4, negative 0.43, 0, 0.43, 0.68, 0.86, 1, 1.11, 1.21, 1.29. They are increasing, but very slowly. That's what I would write down for C. They are increasing, but very slowly. And then use your table to sketch it. So we have negative 2 at 1/25, so really, really close to 0. It has a value of negative 2. At 1/5, so still pretty close to 0, it has a value of negative 1. At 1/2, it's negative almost a half. At 1, it's 0. At 2, it's barely not close to a half. At 3, it's a little more than a half. At 4, it's getting closer still. Finally, at 5, it hits 1. At 6, it's a tiny bit more than 1. At 7, it's a tiny bit more than that. At 8, it's a tiny bit more than that. Finally, when you get to 25, it's going to hit 2. So I think that's enough to see that it's really, really slowly increasing. Like this. Okay, calculate each value. So hopefully we've been playing around with logs enough that you can figure these out on your own. So remember, when you see log base 2 of 32, it's saying 2 to what power equals 32. Maybe you can just think that to yourself in the future. Well, 2 to the 5th power. Part B. Log base 2 of 1/2 is what it says. But you think 2 to what power makes 1 over 2? Where to make it 1 over, it needs to be negative and then 1. C. Log base 2 of 4. 2 to what power makes 4? 2 squared makes 4. D. Log base 2 of 0. 2 to what power makes 0? That's not possible. I can't multiply 2 times itself any times to get 0. Okay, E is changing it up. Let's write this one down. The base is 2. Cubed is going to be the answer to x. So the answer is 8. F is changing it up a little bit too. So it's rewritten as 2 to the 1/2 equals x. We know fractional exponents mean roots. Square root of 2. G, log base 2 of 1 over 16. 2 to what power makes 1 over 16? Well, 2 to the 4th is 16, so it needs to be negative to be 1 over. 2 to the 0 equals x. Anything to the 0 is 1, so the answer is 1. While the idea behind the ancient puzzle is more than 2,100 years old, the symbol log is more recent. It was created by John Napier, who was a Scottish mathematician in the 1600s. The word log is short for logarithm and represents the power to which a fixed number, called the base, must be raised to produce a desired number. The log function represents the inverse of an exponential function, just as the exponential function represents the inverse of the log function. Use this idea to determine the inverse of each of the following functions. And then they want it in y form. So I am going to start by switching the variables, right? We learned that this chapter. If you're looking for the inverse, you switch it. X equals log base 9 of y. But now they want me to get y out of that. So I'm going to use what I've learned. 9 to what power equals y? I mean, you can switch it over if you really like y on the left, but this is the inverse of a. B, switch the x and y. X equals 10 to the y. Use your knowledge of logarithms to change that. 10 is the base. So you can write it as log base 10, but also you don't have to write the 10. You can just leave it blank. Of x equals y, or y equals log of x. That is the inverse of y equals 10 to the x. C, x equals log base 6 of x plus 1. Oops, I didn't change it to y. Of y plus 1, right? Switch the x and y. Change it 6 to the x equals y plus 1. Solve for y. Y would have to equal 6 to the x minus 1. See if you can do D. Okay. 67. Practice your log fluency by calculating each of the values without changing the expression. Okay, in your head. Here we go. Log by 7 of 49. You think to yourself, 7 to what power makes 49? 2, because 7 squared is 49. B. Log base 3 of 81. You think to yourself, 3 to what power makes 81? 3 to the 4th power. C. Log base 5 of 5 to the 7th. You think to yourself, 5 to what power makes 5 to the 7th? Well, the answer must be 7. D. Log base 10 of 10 to the 1.2. You think to yourself, 10 to what power makes 10 to the 1.2? It must be the 1.2. See if you can do the last one. Log base 2 of 2 to the w plus 3. 2 to what power makes 2 to the w plus 3? It must be w plus 3. Hopefully this helped you out. Hope you guys are doing well.